In this example, we will evaluate several more implicit differentiation problems. So let's first find dy dx for the expression given here. And the observation to make is that our first step with implicit differentiation is to differentiate both sides with respect to x. Now on the left-hand side, when differentiating with respect to x, we note that each of these two expressions that we see are both a product of two functions with respect to x. Because y, remember, depends upon x. That's the implicit differentiation part. So on the first term, we apply the product rule. We have the derivative of the first, 2x, times the second, plus the first function, and then we multiply that by the derivative of the second. So we're multiplying this by the derivative with respect to x of y squared. In the general rule of thumb for implicit differentiation, you differentiate that y squared how you would like to, 2y via the power rule, and then you multiply it by dy dx. And then we play the same game with the second term on the left. We take the derivative of the first, which is 1, times the second, plus the first function, and then we have to differentiate the second function with respect to x. So a derivative with respect to x of sine y. So we differentiate the sine y exactly as we would like to, cosine y, and then we multiply by dy dx. And on the right-hand side, the derivative of a constant is always at constant. So at this point, we've differentiated both sides with respect to x. We have two terms on the left which involve dy dx. So we are going to factor those terms out. We will have a 2x squared y of them, and then an x cosine y of them. And the remaining two terms, we are going to subtract over to the right-hand side. So minus sine of y minus 2xy squared. And lastly, we algebraically isolate the dy dx. So we take this expression that's multiplied by it and divide it off both sides. So there's minus sine y minus 2xy squared on the right, and we are dividing this by 2x squared y plus x cosine y. And this expression represents the derivative dy dx. So let's look at another example of implicit differentiation. We would like to find dy dx. We know this is going to be an implicit differentiation because no matter how hard you try here, you are not going to be able to solve for the y explicitly as a function of x. So we differentiate it implicitly. Our first step is to differentiate both sides with respect to x. Now on the left-hand side, when we differentiate with respect to x, we have tangent composed with x over y. This is a chain rule problem. So we take the derivative of the outside function, secant squared, evaluate it at the inside function, x over y. And I should remind you that this is a common formula that we encountered. The derivative of tangent of x is secant squared of x. It was one of our previous examples. So the derivative of the outside evaluated at the inside, and then we multiply by the derivative of that inside. And on the right-hand side, the derivative of x with respect to x is 1, and the derivative of y with respect to x is dy dx. So we have a derivative that we still need to evaluate on the left. So we have secant squared of x over y. And when we differentiate x over y, we're really thinking of it as being a function of x over a function of x, because y depends upon x. So we use the quotient rule. And the quotient rule tells us low d high, and the derivative of the function x with respect to x is 1, minus high d low, so that would be x times the derivative of y with respect to x is dy dx, and this is all divided by the bottom squared. So it looks like a lot's going on here, but all we've really done is we've applied the quotient rule to differentiate x over y. And what that gives us is low d high minus high d low over low squared. And this is equal to 1 plus dy dx. And now in order to isolate this dy dx, what we're going to need to do is algebraically simplify. And one thing we can do with subtraction in the numerator is we can break this up into one fraction minus another fraction.